Now let me briefly talk about other learning aids. So PCA is linear dimensionality reduction. And on the top left, I'm showing you data that's clearly one-dimensional, but it's a spiral, so it's not linear. If you try to construct a linear dimension to capture the data, you'll see that it doesn't capture the data, that it cannot reconstruct the data. The data doesn't lie, on a linear one-dimensional surface. But if you give me a non-linear capability for dimensionality reduction, then I can capture the data well. And what would be my dimension? It would be the distance along this red curve. That would be my feature, and that captures the data quite well. And then the variations of this red manifold that's nonlinear could be treated as noise. Whereas that's not the case if you try to do a linear dimensionality reduction. So PCA would not work with this data. Now, we're not going to talk about nonlinear dimensionality reduction. You can read about it a little bit in the text and, in the literature. Sometimes you have information about the function like, it's rotationally invariant, especially in vision, or monotonicity. So whether or not you get credit should be monotonically increasing in your income, or symmetry. Okay, if something happens when you got richer, then the opposite should happen when you got poorer. So that's an example of symmetry. Okay. So those are called invariances and prior information that you have about the target function, and there are methods for incorporating those into the learning. Now, why would you need to? Because those invariances, for example, rotational invariance, might not be embedded in the data. So you'll see a picture of a tree. The data may not contain the fact that the rotated version is a tree, or the rotated version this way is a tree. But what you can do is you can add those invariant versions and also label them as trees because you know that the target function is rotationally invariant. So that allows you in some sense to augment the data. Those are called virtual examples. Okay? But you can read more about hints. Another perhaps useful task, or if we could do it, is to remove noisy data. So I'm showing on the left the digits data, and you can see some hard examples that have been identified by a very simple algorithm that tries to identify noisy or difficult data. Noisy could either be stochastic noise or deterministic noise. Now, so this blue a circle in the middle of all this red could be treated as stochastic noise. That's just mislabeled. Okay. But then there's a lot of deterministic noise that was identified by these blacks boxed data points, and you can see that it may not be that they're mislabeled, they're just very hard for this two-dimensional feature set and a linear model, let's say. Okay. So if we could remove this detrimental data, noisy data, then we can get the classification boundary on the right, whereas if you kept it, you get the overfit version on the left. Okay, so removing detrimental data can be useful, but we're not going to cover it. I just mentioning it to you. Advanced techniques. Okay, there are lots of advanced techniques, especially for estimating E out. Some of them are more efficient than cross-validation. Some of them are better than cross-validation in terms of convergence properties. Okay, and so you can read about it in the text. Okay. So there's a lot that can be said about learning aids. Okay, and learning aids are techniques that can be used to help any learning model, any other technique that we have. And so what we covered was input preprocessing. Do it. PCA can be useful if you really need to lower the dimension while keeping what should be the important relevant data and throwing away the unimportant small variations, noisy data. Okay, but there are other techniques like nonlinear dimensionality reduction, invariances and prior information, hints, removing the noisy data, advanced validation techniques, lots of stuff that can help learning no matter what model you use. And with that, we're checking out.